Good morning, everyone. Good morning to day 3 of LCN. It's our final day. Nonetheless, we have a full day of program with a particular highlight this morning. That said, it's my great pleasure to introduce today's keynote speaker, Elaine Wong. She's Pro Chancellor at the University of Melbourne and a Redmond Berry Distinguished Professor. She's a leading authority in optical communications and networking with research spanning from low latency networks to human-machine applications. Beyond scientific achievements, she plays a central role in our community, taking various leadership roles, such as chairing the IEEE ComSoc Technical Committee on Optical Networks. Today's keynote explores how immersive applications are driving the need for advanced fiber infrastructures and also the technical challenges as well as solutions that come with them. Basically, this talk exemplifies the evolution of LCN, but also goes back to its roots, and that is local computer networks. And that said, please join me in welcoming Elaine.
Thank you very much, Florian, for that very, very generous introduction. Also, I would like to thank you for the invitation to present the keynote today. It's always a privilege and an honor to be part of that conversation, especially one that helps shape the next generation of communication networks. So before I proceed, I'd like to take this moment to pause and to acknowledge the traditional custodians of the land on which we meet today. They are the Gadigal people of the Kulin Nation. I apologize, of the Eroa Nation. I'd like to extend my respect to their elders past and present, and also extend the same respect to all Indigenous colleagues who are here today. So thank you very much. So without further ado, I'll start with my first slide to rationalize the entire talk today. This is I suppose, a very high-level schematic of the evolution of the different technology paradigms in the last 50 years. And you asked me why 50? Because I wanted to commemorate the 50th anniversary of LCN, but also 50 years ago to this date, I would consider that as the start of the digital revolution. And so at the start, we had the proliferation of electronics, of PC, of mainframes, and that gave rise to what is known as a computation-oriented era. And that gave way very, very soon to a communication-oriented era with the advent of the internet. So that's our first wave of the internet. Very soon, that gave way to the mobile internet with the advent of mobile cloud, as well as supported by big data. Now, and I see that we have a session in the afternoon today, we are in the third wave of the internet, known as Internet of Connected Things or Internet of Things. And here we have sensors, we have monitors, and essentially, almost most of the time, we are taking the humans out from the decision making, if you think about it. And so we're supported by cloud and especially edge computing in this era. So on average, a human, or an adult human I should say, spends about 7 hours of our waking time connected to devices. A teenager, well at least my teenager, spends half of their waking hours on theirs. So a lot of hours. Now, in the very near future, this connection between us and the devices would be expected to be fully experiential, so fully immersive. And we are leveraging technologies such as extended reality, tactile haptics, live 3D TV to have a seamless interaction between the digital as well as the physical worlds. And so all this is underpinned, as you know, by machine intelligence. And so we are soon going to be headed into the experience-oriented era, and if I can hazard a guess, our fourth wave of the internet, known as the immersive internet. And so if you think about it, with regards to these devices that we are connected to daily and increasingly immersive, we must continue to advance broadband access networks and in-premise networks, so local area networks, in which these immersive devices will be connected to. And so hopefully that underpins the talk today. Now, I would like to take a bird's eye view of the telecommunications before we move on so that we're all on the same page. And so I'm going to move horizontally. So this is the physical layer, look at the telecoms network, horizontally from the left to the right of the slide. So we have our optical core, then we have the aggregation network, we have the broadband access network, and then we have our industry, enterprise, hospital enterprise, and our end user networks. So we have our in-premise home and our in-premise business. Now, when you look at the optical core, it comprises of a series and a mesh of routers, of switches, and it essentially provides connectivity from one part of the network to another. The aggregation network, as the name suggests, aggregates traffic to the core and distributes traffic away from the core. Now, the broadband access is important because it provides direct connectivity from the internet to the end users at home in businesses. And then when you think about broadband access, that encompasses both mobile broadband as well as fiber broadband. And in some parts of the world, we still have DSL. We also have cable modem as well. So that all encompasses what is known as broadband access. Now, to the focus of today's talk, which is on the fiber side, the optical access, this is also known as FTTX. So X can be curb, so fiber to the curb, so that's a termination point. X can be home, so fiber to the home. And X can also be businesses, so fiber to the businesses, FTTB. And so when it comes to optical fiber access, we have two flavors. The first one is a point-to-point fiber connection. And the second one, which is more popular because it's more cost efficient, is a point-to-multi-point connection. And as you can see here, the point-to-multi-point connection is cost effective because the same infrastructure, the same CapEx and the OpEx can be shared between many more users, as you can see here. So in this talk, I will interchange passive optical network, which is the point-to-multi-point topology, with FTTX. So FTTX means passive optical network, and passive optical network means FTTX in this talk. All right, so let's talk about the evolution and the progress of broadband access. Now, broadband access networks have evolved from a global average speed of 100 kilobits per second in the early 2000s. So in the last 24, 25 years, it's grown to about 200 megabits per second. But the astounding thing is, in the last 5 years alone, we have seen 500% of growth in terms of the bandwidth. Now, if we deep dive into the fiber access, and here, I want you to maybe first, I will actually give you an overview. Here we have 4 regions whereby we have the global market share, and this data is taken from Omdia 2023. And I apologize if your region's not here. It was not possible to put everything on the one slide. So what I want you to do is to focus on the gray composite bits. Yeah, so the gray one, or the gray ones here, pertain to the fiber to the X global market share. And 2 things can be drawn, can be observed from this slide here. The first is that the FTTX market share is actually different for different regions around the world. And it really depends on the legacy network, the legacy broadband network that's already deployed there. So for example, in Western Europe, you will see that the purple, what is the purple? The purple is DSL. That's your dominant broadband access. And so the FTTX here, especially in the early days here, is not as dominant. Whereas in North America, the dominant broadband is actually cable modem, regardless of the region. The second observation is that the FTTX market share is expected to increase due to these legacy networks being replaced. So these are the two observations. Now, when it comes to the global market share, by 2030, FTTX is expected to constitute 77% overall. And so if we look at the actual subscriber count, here again, the sources from Omdia 2023, it shows that globally, FTTX subscribers have surpassed 1 billion in 2023. And with a compound growth rate of 7%, the expectation is that it will surpass 1.4 billion by 2028. So if you're sitting there and you go, yeah, these are big numbers, but how does it translate into dollar signs, the revenue? So here, I've shown you the revenue just for a sliver of the PON or the FTTX here, and we're looking at the equipment, okay? So the PON equipment, and here we've combined two families of standards, the IEEE as well as the ITUT. So these family of standards are applied and deployed at different regions of the world. So one thing to note is that the global PON equipment revenue is forecast to reach 20 billion by 2028, and further growth is expected to reach 44.5 billion by 2032, an astounding compound annual growth rate. And so the question is, well, if you were me, you'll be sitting there thinking, hang on, I thought, broadband penetration would have saturated by now, 25 years on. So why are we seeing this growth? Well, it comes down to three factors. The first is, as I've said, legacy networks like DSL, cable modem are gradually being replaced by fiber technology, in particular the passive optical network point-to-multipoint technology. The second is that point technology is actually finding new opportunities in new market segments, which is one is fiber to the room, which we'll talk to today, and other markets, for example, smart agriculture, as well as smart grid communications. Now, thirdly, the current generation of PON that's already deployed is itself being replaced by a newer generation of PON at a larger speed, or broadband speed. So let's talk about these generations of passive optical networks very quickly. And so here I have plotted the many generations of PON technology from 1990. And because we have to support new applications that are increasingly more bandwidth intensive, with new KPIs and new quality of service requirements, quality of experience requirements, new generation of PONs are introduced every 8 to 10 years, as you can see here. And every time a new generation comes out, there will be likely 4 times the bandwidth capacity of the previous generation. But having said that, globally now, the deployed PONs are predominantly the first generation, so the E-PONs and the G-PONs, although they are being gradually replaced, as I've said, with the 10 gigabits per second flavor. And so with that, hopefully that has set up the impetus of where we're heading, which is fiber to the home and building. Now, so that we can be more on the same page, let me talk about some of these drivers as to why we want to extend the fiber from the broadband access into homes. Okay, so shown here are the connected devices and the applications in households across time from 2020, 2025, and onwards to 2030. Now, as you can see, comparing 2020 to 2025, the average number of connected devices per household has doubled. And if we take it beyond 2025 to 2030, the average number of connected devices would have increased by another 80% to 44. So if I look at 2025, I would like to show of hands, how many do you think in this audience would have 25 devices at home? Easily. Easily, right? I mean, I have 7 on me today upstairs in the hotel room, including smartwatches and things like that, right? So easily, 44, I think it's a little bit conservative. I would say in 5 years, you know. Anyhow, so besides the rapid growth in numbers, the type and the capability of these devices are also evolving. For example, take today, right, 2025, we have IoT devices, we have our smartwatches, for example, our sensors, our 2D, 4K smart TVs. Those are all going to evolve to tomorrow's immersive devices. So we're going to have ultra high definition 8K TV, we have got 3D live TV, we have extended reality headsets, we've got VR headsets. So we're going from 2D to fully immersive 3D experience. So not only just the numbers, but the type and the capability. And so before we talk about the capability, let's talk about extended reality. So what is extended reality? So 3GPP defines extended reality as all real and virtual combined environments and associated human-machine interactions generated by computer technology and wearables. And extended reality is really an umbrella term for 3 intersecting immersive technologies. And the first one is augmented reality. And it's been here for quite some time now. Who plays Pokemon here? Come on, you can admit you play Pokemon. No? No? This is LCN, really? No stereotyping, I apologize. Okay, so augmented reality means that here we have visual text, images, animations overlaid on top of a real world. And to access augmented reality, we need AR glasses, we can use our smartphone, and smart iPads and things, and so on and so forth. The next technology under the umbrella of XR, extended reality, is mixed reality. And this is a more advanced version of augmented reality in that you can blend real and virtual objects, allowing the digital and physical worlds to exist together. And what this means is that the virtual object can be placed spatially to a real object. And as you can see in this example here, you can see that I can place the virtual object behind a real sofa. So I'm not simply just overlaying on a real image, I can place it spatially in relation to real objects in the room. And to access mixed reality, I need to have specialized headsets, and those are fairly dear at the moment, not enough for consumer market or great adoption or wide adoption. And so the next one is virtual reality, which I know you all know. It is a full immersion of users in a closed, controlled, and simulated virtual environment. And as with mixed reality, you do need a specialized handset. And so with that down pat, let's go back to the slide before, and now I want to talk about the requirements of these immersive technology. Let's peg our conversation to what's happening today. So today, our 4K video requires about 50 megabits per second bandwidth. But if you go to 2 years later, 2027, if we talk about 8K video, we will need 6 times that, so at 300 megabits per second. And beyond 2027, when we look at 2030, 2034, in fact, we will expect to have XR free viewpoint as well as live TV, 3D TV, which requires massive, massive bandwidth of 2 gigabits per second, of 5.5 gigabits per second. And for those who don't know, XR free viewpoint means the ability of a user to change their vantage points in a scene. So I can change to be behind the goalie, okay, of a football match, or I can change my vantage point to be one of the audience in the first row. So that's what XR free viewpoint is. And so I'm sure you have seen the big billboards in Times Square and in big squares in China and in Japan, where you have this 3D sort of objects reaching out. And imagine having 4 or 5 of these 3D live TVs running concurrently in each home. And so each household will have multiple of these concurrent applications. And can you imagine the amount of bandwidth that we need? And so aside from high speed, yes, we do need that. There are other user experience requirements that we also must meet, including low latency, high reliability, and uninterrupted, consistent level of connectivity. So very, very strict demands and high demands of our network. And so to recap, the growth in numbers, the variety of devices, and the evolution of device capability from 2D to immersive 3D gives us the impetus to continue to advance fiber to the X. Not only that, we need to extend fiber solutions into the buildings, into the homes where these devices are connected, and one of which is the fiber to the room technology, which we'll talk about now. Okay, so we've established that in the near future, devices will evolve from 2D to 3D, and XR application, if I take that application out of all the applications we've talked about, the immersive applications, it can be delivered via 3 different levels of user experience. And shown here is a table that talks to the data rate, the bandwidth, as well as the total latency of these 3 levels of user experience: fair, comfortable, and ideal. And so as you can see here, each level of user experience imposes a different demand on the network performance. So if you take the ideal QoE, for example, if you look down at that column, for me to deliver a 8K, let's start with 8K video frame at 60 frames per second, I would need to have a data rate of at least 360 megabits per second per stream. So imagine you have got multiple of this at home, but with that one stream, 360 megabits per second at least. And I need to have a bandwidth of at least 1 gigabits per second, and it all has to be delivered in at least 8 milliseconds, okay? So with that, I'm gonna tell you a piece of good news and a piece of bad news. The good news is, remember how one stream is 1 gigabits per second, right? So how do we manage all of this at home? The good news is field trials of 50 gigabits per second, passive optical networks, has commenced. Some of them have completed last year. Those are in red. And we are seeing some commercial deployments emerging already in 2025. So that's fiber to the X at 50 gigabits per second. So lots of bandwidth. So that's the good news. The not so good news is that now we have a disconnect between what's happening externally in the broadband network and what's happening internally at home. So our home networks are, well, for me anyway, is predominantly distributed Wi-Fi based, right? Wireless LAN. And even if I go 6E, maybe 7, I'm still going to be hit. Imagine if I have like, was it 44 devices? I can't remember the number, but 44 devices. I'm gonna be hit with unavailability, unreliability. And so we really have to think, how do we support these 44 devices, many of which needs at least 1 gigabits per second and 8 milliseconds delay, to ensure that we have end-to-end from in-premise to broadband all the way to the core and back. So that's the dilemma. And so the last 100 meters really is now the performance bottleneck that impacts user experience when it comes to immersive application. And so the solution is to extend our fiber into the room, all the way, not just the building, but into the room via the fiber to the room technology. And the FTTR fiber to the room technology adopts the same point to multi-point topology because there are obviously benefits there. Secondly, we have to find a way to intelligently coordinate bandwidth resources between the external network and the on-premise network. And if you want mobility of your devices, you would still need an advanced Wi-Fi as the last 10 meters. And so we have to do all of this to ensure that we meet quality of experience requirements. Okay, so talking about fiber to the room, the standards body ITUT, study group 15, has looked at fiber on-premise network solution, so that's G.15, that encompasses exactly what I've said. An external FTTH, so external PON. In this example, it can be a 50 gigabits per second PON. That you combine with an internal fiber to the room. So each of these termination is one single room. And if you want device mobility, integrate that termination with a wireless access point. So in total, we have an external fiber to the home, an internal fiber to the room, and then we have our last 10 meters with a wireless LAN, an advanced wireless LAN. And so each room, as I've said, is supported by, ideally, one integrated subordinate fiber unit. So that's the termination of the fiber to the room network, and a wireless access point to avoid interference. Okay, so you'll be sitting there thinking, okay, great, this is a great solution. We have lots and lots of bandwidth. You know, we've got an external 50 gig, we've got an internal 10 gig, and then we have an advanced Wi-Fi. What about latency? You know, how do we solve the latency issue, right? So if you think about it, the fiber has a limit to its latency. The processing has a limit to how low you can make the latency. So how do we get around this latency of 8 milliseconds? That's the yardstick for the high-level quality of experience XR. What I'm going to do is I'm going to use a use case to show you how we get around the latency to meet user experience requirements. So this use case that I'm going to talk about is immersive XR, but we're going to stretch it a little bit. We're going to extend a little bit of not just a passive immersive XR, but one whereby the human is going to control a robot through immersive XR. And this is how it works. So say we want this application or this use case for surveillance, yeah? And I am a security officer, and I'm off-site from where I want to monitor and surveil. And I have a robot, a roving machine or a robot in a separate building where I need to monitor. Okay, so I will wear a head-mounted device, so that's the headset. And I will use that to monitor rooms in a separate building where this robot is. So that's the premise. The human and the robot will be in different buildings, and they will be supported by different fiber-to-the-room networks. I will have an application software here at the central office of the external FTTH. So that's where I'm going to put my app server. And I'm going to use that to coordinate any human-robot pair. And I'm going to use that to somehow circumnavigate the latency requirement. Okay. Now, with the security wearing the headset, so I'm wearing this headset. It's an XR headset. My head orientation, or any head orientation, will generate real-time orientation data. And this data will traverse to the edge server in the central office. The app software in the server will then translate the orientation data that I've just made into commands to orientate the robot head accordingly. So the robot head is embedded with a camera, and the camera will send real-time video frames back to the edge server. So ideally, when I wear this headset, when I swing my head the robot will swing its head. It will capture frames or capture video frames from where it's looking, and that will send it back to me, and it will be displayed on my headset, ideally. Okay. However, there's no such thing as a free lunch. The head orientations of the human and the robot is not synchronized. There's actually a time lag between me swinging my head and the robot head swinging, simply because there is a geographical distance between the human and the robot. And the servo motor that you see here, the servo motor of the robot here, which is the neck area here, that controls the robot head, has limited speed. So I can only swing my head that quick, you know, and it will be limited by how fast the robot head can swing. So the implication is when I rotate my head, and if there's a time lag, the scene will only come into my view a few seconds later. And if this time lag is more than 20 milliseconds, then physiologically, I will detect a loss of synchrony between swinging my head and seeing that scene coming into view, and that will cause cyber sickness. And so to satisfy immersive XR user experience, it is really important for us to synchronize this human and the robot head movements, and that's what we're going to do now. Okay, so to do that, there are a couple of things that we need to do. As I have foreshadowed earlier in my first slide, a lot of it is underpinned by machine intelligence, but the question is, what do we do with machine intelligence? And so here, we want to predict my movements. I want the edge intelligence here to predict what I am about to do. Once it does, the app software is going to translate my predicted orientation into commands. It's going to send ahead to the robot, and then the robot will orientate its head. The camera will actually then capture XR video frames. It will go back to the app server to be rendered, and then back to my headset, syncing it perfectly. So that's what we're trying to achieve. Predict my head movements, send the control signals ahead, get the robot to turn, send XR frames back so that it then will align with what I'm seeing in my headset. So how do we do that? How do we do the prediction, and how do we do the preemption of sending these control signals, and how do we make sure that it's in perfect synchrony? So first, we need to do some experiments to really understand the data, the orientation data from the headset, and also the XR frames from the robot. So very quickly, this is our setup. We have conducted experiments to conduct empirical data to understand these characteristics. The green is the orientation data from my headset, and the purple is the XR frames from the robot. And here in the setup, we have Wi-Fi interfaces between the headset and the app server, and the app server and the robot. And the app software, as I said before, uses real-time orientation data from the headset to control and orchestrate the robot. And the robot will then send XR frames back to the app server to be rendered and displayed on my headset. Okay, so let's look at some of these traffic characteristics. So this is really interesting. So the app software actually captures my human head orientation as Euler angles, and there are 3 components, right? So we have the yaw, so yaw, 180 to minus 180. We also have the pitch, so essentially that's up and down, and then we have the roll, again 180 to minus 180. So 3 components, 3 orientation components. And then what we did was, we did a little bit of analysis of the captured data. We looked at the inter-arrival time of these orientation data from the headset to the app server, and we found that it arrives approximately every 15 milliseconds. So we're going to use that knowledge, yeah? So these orientation data, the 3 components of which come to the app server every 15 milliseconds. Now, if we plot the time series, or rather the angular position of the 3 components versus time, you will see that for surveillance, at least for the surveillance case where we're actually snooping around and making sure that everything is okay and safe, the orientation components, all 3, actually do not show any trends or seasonality. In fact, the angular positions randomly swings, between the highest and the lowest Euler values for each 3 of the components. And if we look at the autocorrelation, and I didn't plot it here, I didn't put it here, it actually highlights that all 3 of the orientation components have actually long-term memory. And so if you're into machine learning, and especially sequential and sequence prediction, you know what that means, long-term memory. That means that we can use this tried and tested models here to predict all 3 components of our future head orientations. And I won't go through them, but they're here. And so we use the collated data, the harvested data, to train and validate our models. So we've got 3 models for 3. So each of these will have 3 for the 3 orientation components. And so in total we have we've got 12, And so we use that to train and validate the models. And we want to ideally predict each of the 3 orientation components even before it occurs. And our prediction horizon is 6 samples ahead. We want it to be that far ahead. Remember, each sample is 15 milliseconds because it arrives every 15 milliseconds on average. So 6 samples is 90. So we're going to predict 6 samples ahead. And then we're going to compare the prediction performance of these 4 models as a function of orientation speed. So how fast I can swing my head in the 3 angles, or different angles or components. And these are the normalized root mean square error for the 4 models as a function of head rotation speed for the first orientation component, which is yaw, pitch, and roll. And a few observations you can see here. As head rotation speed increases, so if I swing my head faster, obviously the prediction performance degrades. It actually makes sense, right? So we are less able to track sudden swings in head movements. So what this tells us is this is jolly good and this well, depending on the use case. For surveillance, I think it's fine, But for, I don't know, gaming, where you have got to, have jerky head movements, I actually don't game, but I'm sure a lot of you game. You might tell me that, look, maybe, that's not going to work, Your prediction models aren't going to work. So the second thing to note is that the pitch component, so the pitch is the up and down, the normalized RSME of this is actually much lower. It's actually 10 times lower than the yaw and the roll, and that's because it's got a smaller swing. So the prediction is much better. And finally, bi-LSTM performs the best because it takes some recent samples in addition to the whole range of samples that you use to train. So it's more robust to temporal dispersance. Okay, so with that, so the results here are based on a prediction horizon for 6 samples, right? Ideally, we want it to be a longer horizon. And so we've done a sensitivity analysis whereby we want to look at the normalized RSME versus rotation speed of the head versus prediction horizon. Because since human head movement is many times faster than the robot, the ability to predict longer horizons especially is really important so that we can maintain synchrony at all times. As shown here is a sensitivity analysis for the normalized RMSE versus head movement in terms of speed versus prediction horizon. And again, a couple of things can be drawn. As you can see here, the RSME increases, which means the prediction performance degrades as a function of head rotation speed, as a function of horizon prediction or prediction horizon. So that's not anything surprising. But what we can do is, if we know and if we can measure the time lag between a human and the robot it's controlling, if I can measure that time lag, then I can predict, or I can choose my prediction horizon, yeah? Because it's every 15 milliseconds, right? So I can choose my prediction horizon at initialization and ensure that it's trained to that prediction horizon and predict to that horizon. So with that, let's talk about the second thing that we collect. So the first one was the head orientation. The second thing is the XR frames from the robot. And so again, we want to collect it so that we can have knowledge that we can use in our prediction. So first, we plotted the interframe arrival time. Again, it tells us now that the frames arrive once every 1.76 milliseconds. Next, if we plot the frame size distribution, it tells us it has a gamma distribution. Now, knowing the frame size distribution and the interframe arrival time is really powerful, because I can use that to predict how much bandwidth I can give that robot so that it can send its XR frames without waiting. Again, it's all about latency, yeah? So knowing these two parameters, I can go, you need that much bandwidth at that particular time, and so the robot will start sending the frames without delay. Okay, so we're gonna put it all together. So our purpose is, what is our purpose? So our purpose is to ensure that there's perfect synchrony between the human and the robot. And our purpose is to ensure that the XR application maintains below the user experience levels, okay? And from memory, it was 8 milliseconds for the highest level, okay? So we propose a human-machine coordinated dynamic bandwidth allocation scheme, and it does three things. It predicts human head orientation before it even occurs. It sends ahead this commands to the robot so that it can spin its head according to the prediction, and then it can predict and allocate bandwidth to the human head orientation data, the XR frames, and also the background traffic without delay. Okay, so, right, so shown here is the scheme of the human-machine coordinated scheme. We have the edge server. Again, that is to predict the future human head orientations, the bandwidth of the transmitted predictor-oriented commands to the robot, and the bandwidth of the incoming frames. And we also have a main OLT, whereby it coordinates the bandwidth allocation between the external PON, the internal in-premise networks. And at the moment, we have not included advanced Wi-Fi, but the advanced Wi-Fi coordination will also come in here. Okay, so because we couldn't do the experimental verification for this, we started looking at the simulated network for now. And here, our simulated network tells us that our external architecture has, or is servicing 16 different homes at 20 kilometers away from the center at 50 gigabits per second. And within each home, it services 8 different rooms, so 8 different termination points with a wireless access point integrated. And it's 100 meters inside the home at 10 gigabits per second. And so in total, we have 128 terminations, and we have 56 pairs of human-robot XR collaborations. Okay. And the human and the robots may reside in different homes, which means that they are on different FTTR networks. And the remaining SFUs, so subordinate fiber unit and the wireless access pair, will support background traffic. So we have a mixture of background traffic and human-robot XR collaborations. Okay, so now we want to test through the simulated network whether the XR traffic that's generated in this network will actually satisfy, I think it was called fair, comfortable, and ideal user requirements. Okay, so let's look at this. So this is my third last slide. So here we have end-to-end latency, and we're going to start talking about the fair user experience latency, and that is at, let me just see, 20 milliseconds. And as you can see here, we compare the latency of the XR frames, and we compare the frames that are implemented through the proposed scheme, which has prediction, and also through another scheme known as the limited service scheme without prediction. And as you can see here, for fair user experience, the proposed scheme, or rather the XR frames of the proposed scheme, satisfy the latency requirement. Now, if we look to the comfortable and the ideal user experience case, with 15 milliseconds and 8 milliseconds thresholds, you can see that the XR frames from the scheme that does not have any prediction, only the fair user experience latency is addressed and met. However, using prediction, all levels of user experience is satisfied. And so the next steps for us is to conduct experiments to verify this. Especially, we want to verify the synchrony, doing all the prediction and all the preemption, the synchrony of the human head and the robot orientation. Okay, that takes us to the summary, my last 2 slides. So today, in the last 50 minutes, we've talked about the impetus of why we need to still look at broadband access and why we need to extend fiber into the premise. And that is, in the near future, we'll be looking at immersive experiences, immersive applications that we need to support as we head towards a physical virtual world that is seamless. We've looked at how, for the use case of XR collaboration, whereby a human controls a robot from afar, of how we implement fiber to the room and ensure that there's synchrony in the human and the robot heads, and that we can predict and allocate bandwidths to meet user requirements, especially the latency. And in conclusion, I like to say that our networks is supporting applications that's growing in complexity, in heterogeneity, and it's getting more and more diverse, more bandwidth intensive, lots of KPIs. And it goes without saying, machine intelligence will underpin this, but the question is, how do we use this carefully, but also responsibly? And if you can allow me one last slide, we started the whole talk by looking back 50 years. I'd like to end by looking ahead, not quite 50 years ahead, but next 5 years to 20 to 30. And shown here is the tech life cycle. And by 2030, VR headsets, our smart homes, and our 4K TVs will have reached maturity. And we would see the early signs, the early uptake of live 3D TV, the early uptake of metaverse, which is, again, physical digital world seamless. And we're going to see an uptake on 8K video. So what this means is that I don't think we can, rest on our laurels. There still needs to be lots and lots of investment, a lot of focus on end user networks, whether it is local area networks, whether it is in-premise networks, whether it is broadband networks. There still needs to be this push. And hopefully, and we were talking about, bringing this conference back to Australia. So hopefully, foreshadowing, in 5 years, I might still be talking about fiber to the home and the broadband access, and I'll be giving you a update on this slide here. So thank you, everyone, for paying attention, for coming in after the fun night last night. Thank you, everyone. Thanks.
All right. We have time for questions. Are there any questions? Yes, of course, there is one.
Thank you for a very interesting presentation. Could you comment on the competitive technologies as a result of millimeter waves, smart surfaces, and steerable beamforming especially for the last 10 and 100 meters?
Yeah, so I am not personally in the area of indoor 5G, or if you talk about millimeter wave, indoor 6G, but the idea here is that I think not bringing fiber into the rooms at least for devices that do not need mobility is, how do I phrase this? It's a no-brainer. We have to bring fiber in. As to the question whether it's going to be advanced Wi-Fi, whether it's going to be, indoor 5G as the last, 10 meters, whether it's going to be Li-Fi, so optical wireless, that remains to be the question. I do think that indoor 5G and even 6G, if we're going down that path, does have its use cases, perhaps first in an industrial environment, more enterprise, rather than residential, as we've talked about. Yeah. Thank you.
Next question. Yes, please.
And I forgot to thank the people that has contributed to this work all along. I apologize.
Thank you for the talk.
Yes.
So it's very interesting. I'm personally specifically interested in this robot examples you raised. I was just wondering, if the link you're using is dedicated to the specific robot use case, or is it shared also with other services?
So in the simulation that we've done, it is actually shared with background traffic. So, there will be other people in the same building, logging onto the internet and doing other things. But the whole point of predicting bandwidth, let me just go back here. The whole point of predicting bandwidth and pre-allocating that is so that you can share the network. So it's almost giving priority to the robot. So it is important that, obviously, cost is sensitive, when it comes to end user networks. So the idea is to share that network, but you prioritize by predicting the bandwidth that you need and pre-allocating that, to get around that delay. Yeah, that's a great question. Thanks.
Right. Can you hand over directly?
You talked about, great talk, by the way. You talked about the increase in speed in devices. Can you talk about what you think the cybersecurity aspect of that will be? Are we going to be putting endpoint devices to protect the home at that point of presence for intrusion, or how are we going to defend all these devices?
Yeah, so we have a separate, so I suppose there are two answers there. I think we will see a mix. And I don't think we can get away from not securing our devices, again, depending on the use case. We've had a raft of work looking at the intrusion of someone intercepting so which side? So human control, the control data. So essentially you can, because it's physical layer, you can intercept and you can poison the control data so that your robot does different things. And so I can't think, let me just think what was the solution. The solution was to use concept drift, and I don't know whether it's familiar to a lot of people. So concept drift is a technique that you use to detect anomalies in your traffic. And so there will be signatures of the intended user, the human, and signature of the intruder, right, that you can detect as concept drift. And once you detect that, and the issue is how fast can you detect that and how fast you can intercept. But coming back to your question, I think there needs to be this mixture, because we pull down applications, we introduce applications, it changes throughout the day, the seasons. There's no way you cannot introduce some of these security elements within that device itself. It's just the whole network is getting so dynamic, you can't plan ahead,
Thank
you
you.
can no longer plan ahead.
Do we have more questions?
No one ever chucks that thing, does it? Everyone's so ginger.
Now we
Okay, you
have
got to chuck. Okay.
We have a chance.
I'm not good at this, so thank you for a great talk. And actually, I'm from software engineering field, so
Yes, yes.
I'm curious that okay, so suppose that such fiber to the room and will be implemented more, and then what about the application development work? Could be a very challenging to manage such a high complexity of in-house network, but also even
Correct.
in-room network complexity.
Correct.
So
exactly.
how software applications could, and particularly end-to-end, and so.
Yeah, no, that's a great question. And I didn't get to go to my last bullet point. I think we need to start segmenting these networks and to ensure, you see, that key part in managing complexity, orchestration, and user experience. I think we need to embed these intelligence everywhere. It's almost a distributed intelligence across the network. And if you look at enterprise, you don't really need it to go to the core. You can keep it within the enterprise. So I think the idea here is to use intelligence, but to ensure and to really plan and optimize where you put these intelligence at within the network, to orchestrate, to control, and to manage the complexity. But yeah, that's another great question.
To manage more intelligence.
Yeah. Yes.
Wow,
That's right.
Thank you.
Another one, yes, sure.
Hi, yeah, it's really, really interesting. What I was thinking is we have a latency problem that you talked about. Have you thought of any way so that we can compress and encrypt those extra frames rather than increasing the bandwidth?
So it's already encrypted.
It's already encrypted.
Yes, correct. Yeah.
And is there any way we
so
can,
you can see,
compress those data so they will travel fast? I don't know.
So one other way, we've been looking at, let me just double check the frame size. I do believe this one here is already compressed. One other way is to have parallel channels. So at the moment, we've looked at just one channel up, one channel down. Yeah. The other way is to, parallel processing, yes. So to have different wavelengths, but again, managing different wavelengths down, different wavelengths up.
That's right.
Yeah, that's a trade-off, yeah.
Right.
Yeah.
So this is your last chance.
And then we'll hear where the conference is going to be next year.
All right, everything's settled. Everybody's happy.
I'll
so
be here till the end of the day,
yes,
so
that,
happy to.
that was my saying.
Yeah.
If you have any further questions, please approach Elaine and get in touch, I guess. So let's thank her again. And of course, we have a little surprise for you. And sorry, Elaine.
Oh. I thought the surprise was
no,
where are we going next year?
The surprise is
Thank
actually
you.
for you. So
Oh,
first of
thank
all, we
you.
would like to
Thank you very much.
show our appreciation for you being
thanks.
here.
Thank you.
And
Oh,
we
where's the?
even-
Oh, do you want to take a camera? Yeah. Take a photo. Thank you. Thank you, everyone. Thank you.
And we even have a little
Oh, wow.
gift for you,
Thank
a
you.
notebook.
Thanks. Thank you. Thank you very much.
Thank you
Thanks,
so much.
Florian.
Thank you for being here.
Thank you, everyone.